Welcome everyone. In this video I would like to return to this DC-DC converter again. So this is the SZBK07 DC-DC converter, 300 watts, and it's a very nice compact sized DC-DC converter. So it has the two MOSFETs here, and this is the buck controller here, and our main components are the two potentiometers here, which are missing, but I have it here. So there are two potentiometers here, 100 kOhm trimmer potentiometers, which are used to control the current, that's the CC, and the voltage, that's the CV, on the output of these guys, these three. They are identical. So what I did in the previous videos and previous demonstrations is that I manipulated the voltage across the CV potentiometer or the current, and then by that I was able to change the output voltage, and we could do some digital manipulation of this. So for example, I was using a microcontroller together with the digital potentiometer, and I was using that digital potentiometer to change the output voltage of this thing. And the thing is that we cannot directly put in any kind of potentiometer here, and I am referring to digital ones, because the voltage across the potentiometers, these guys here, is always the same as the output voltage. So the more you increase the output voltage, the more you increase the voltage across this component. And the digital potentiometers only work, most of them only work up to 5 volts, and they just simply die. And of course we don't want that, because it's an expensive component, so we would like to avoid that. But by using a very simple trick, we can change the range of the input voltage that is needed to manipulate the output voltage of this thing on a full scale. So finally I was able to use a digital potentiometer, and I was able to control it. And to see that in action, check the video in that corner. I put there a link, and you can see that by a simple potentiometer with a microcontroller I was able to change the output voltage. So that was nice. So I work with this circuit with the following principle. So the most of the time I will need this for a Peltier cooler, and the current running through the Peltier cooler obviously can be adjusted by increasing or decreasing the voltage, the input voltage of the Peltier cooler. So what I do on this board is I maximize the current potentiometer, so always the maximum allowed current will flow through the device, and I mean through the device which I attach to the output of this DC-DC converter, but that current obviously depends on the voltage. So I just want to manipulate the voltage, and we did one step towards that with this kind of circuit. So what I did here is, as you can see, I removed the voltage adjusting potentiometer, and technically I haven't removed it because I put it back in a form of this thing, so it's connected in the same way, because this is connected as a rheostat, so it's a variable resistor here and not a voltage divider. But what I also did is that we have this 10K potentiometer, and on this side of the 10K potentiometer, if we modify the voltage between 0 and 5 volt, which is the output voltage range of digital potentiometer, or the PWM output of your microcontroller, we can control the feedback voltage going to the feedback pin of this buck controller, and we can change the output voltage of the device on the full scale, and that's very nice. But that's not always the thing that we want. So finally, after this much talking, I arrived to today's topic. So what I want to show you is two different things. First of all, I already have the circuit assembled to that purpose. Is sometimes you want to restrict the output voltage of the DC-DC converter in between two values. Let's say you want to restrict it to 6 to 12 volts, and yeah, you want to drive an LED or something, and you want to dim the LED, then you might want to use this voltage range. Or you have some other devices where you just want to modify, for example, one potentiometer, but you don't want to go outside of the range that you define. So for example, if you would just use the built-in potentiometer of this, and you have, let's say, 24 volts of input voltage, then when you change the potentiometer, you will be able to go through almost the whole scale, because this device is almost working at 100% efficiency, so you almost get the full voltage on the output, and that's very nice. But sometimes you don't want that, and what you can do with this trimmer potentiometer is you can only change let's say the volt direction. So either you go down or go up, but whenever you hit the top or the bottom of the scale, you will be always at the minimum or maximum voltage, which is allowed based on the input voltage, and of course the characteristics of the DC-DC converter itself. But that is never restricted to your own value. So what I did here, I put together a circuit here, and that is a very, very simple circuit. And what it does is that it only works between 6 and 12 volts. So now our input voltage here, it's coming here, that's 12 volts. And I can show you that right now by turning on this. So we have a third multimeter here, and I can show that the input voltage here should be 12.69. And here it's 12.62. So 69, which is shown on the power supply. So this is our input voltage. And then what you see here is the current here. I will explain it in a second. And here you see a voltage value, which is the output voltage measured on the DC-DC converter. So what we do here is, this is a 5-volt power supply. And the positive side is connected to a 50 kOhm potentiometer in a rheostat mode. So the rheostat mode basically means that you put the voltage in on this side, and then you connect together these two other pins, and then you continue the circuit from these joined pins. And then that's what happens here. Obviously you will find the drawing on my website, but I explain it here as well. So then the continuation of that potentiometer is another 100 kOhm potentiometer. I think you can see it. And that's also in a rheostat mode. So again, from the 50K potentiometer, the circuit continues here. These two guys are connected together. And then we continue our way into this clip, which goes into this now current meter, and now it shows 205 microamps. And of course it continues here because we have serial connection when we have a current meter, and then it ends up here. I can try to show you at the red wire, which is going directly or almost directly to the feedback pin. To the feedback pin of the buck controller. So what happens here is, if I change this 100 kOhm potentiometer, this is not changed. If I change the 100 kOhm potentiometer, now this voltage from 6 volts should go up to 12 volts. And it should stop there. So we reached the top. So what is happening here is that we define an upper limit here with the trimmer potentiometer, and that I defined by the by reading the output voltage and turning the screw here. And then I go back to the 50 kilo ohm resistor here, or sorry, 50 kilo ohm potentiometer, and I adjust the lower voltage here. I check it. And then I also have to adjust the 100 kilo ohm to match my requirement. And then I just do this iteratively, so I find the perfect combination of the settings. But at the end, what happens is that the 50 kilo ohm resistor will be at fixed position, and also the trimmer potentiometer will be at a fixed position, and the only potentiometer that you choose to change is the 100 kilo ohm potentiometer, and you change it on its full scale, so from 0 to 100% resistance basically. So now we are at 100 kilo ohms, and if I go back, then we are at technically 0 kilo ohms, so no, this acts as a wire sort of. And you can also see it on the current, that now we have a lot of current running through this circuit, but when I look at this, it's much lower current. And we can also check something which might be interesting, is that I want to show you this, that we are controlling this with the current and not with the voltage, because now we are at the max potentiometer value, which is now giving us 12 volts. And let's say I want to change, want to see the voltage across this whole circuit. So first of all, if I check, if I could, so first of all, we want to check the voltage drop across the two potentiometers, and you see that it's 3.8 volts. However, the input voltage here is 5 volts. I can show it as well. So you can see. So we drop the voltage here with the potentiometers, and we get 3.8. And actually I calculated this, and here at these settings I actually went in the other way, that I checked what is the current on the wall circuit, and now that's 36 microamps. And then I knew that the resistance of this wall thing is 104 kilo ohms here, and then that gave me 3.8 volts. And then I changed this guy here, and now the resistance of the circuit was 18.5 kilo ohms. So indeed this went back to nearly zero, and by using the Ohm's law, that gave me the 3.8 voltage, 3.8 volts as a voltage. And I can show you this. This should be very easy. So I remove this from the circuit, because obviously we don't measure resistance under voltage, and I just put this here. So now we should be able to read 18.5 kilo ohms roughly, and it's there. I hope you can see it in this display. And now I change this to the other way, where we should measure 104. And there you go. So these are the settings that you want. So when you want to reach 6 volts, so I show you. So when you want to measure 6 volts, you have to inject this amount of current to the circuit, because the voltage will be always the same between the two levels. You want to inject this amount of current, and when you want to have 12 volts, obviously you need less, so 36 microamps. And actually that was the same thing which happened when I showed it with the digital potentiometer. So as I increased the output current in the system, then I decreased the voltage of the DC-DC converter, the output of the DC-DC converter, and that happens here as well. So now I drop down the resistance of this thing, and then it increased the current at same voltage, and then we got a decreased voltage here. And now, as an exercise, let's say we want to have the voltage in between 4 and 8 volts. So I show you what happens, but basically you need just two resistors. So I just mess up everything here. Just turn it somewhere. So I turn both potentiometers to the minimum, so counterclockwise. So I show you that in this direction, not this, but this. So this. So now, as you can see, we have a zero output voltage, and here we have too high current running through this thing, and that is because we zeroed out the two components here. So what we should do is, first let's try to find that 4 volts. So now I just try to increase the 50k potentiometer here. So all I just try is I try to find the 4 volts. So now I'm increasing it, and now I'm decreasing it. So let's say this is the 4 volts. But now if I move with this, with the middle, since I defined the top voltage, or yeah, so the ceiling of this range with the trimmer potentiometer, and that was 12 volts, that is still 12 volts. So now I should find a screwdriver and move this back to 8 volts. So I check the CC trimmer, and I start to figure out how to decrease the output voltage. So now in this position, when they are closer to the bottom, I'm turning the screw counterclockwise, if that helps. So let's say that you have to be careful with this screw. So let's say that that's 8 volts, and now I change this thing, and now you see that we went under the 4 volts. So I again have to increase the resistance with the bottom. So as I said, this is an iterative process. So that is 4 volts. So now I move back with this, and we reached 8 volts. So this is literally the max. So I cannot turn it. So we reached 8, and for some reason this is a bit unstable, but that was 8, and this should be still adjusted a little bit. So this was 4, and I go back up, and this is 8, and this is 4. So this is very easy. The voltage source here is 5 volts, but basically you can use any kind of voltages. You just have to readjust for your own input voltage. So if you change the input voltage, I can do that. So now my input voltage is 3.3 volts on this rail here, so I have to readjust it, but that's not a big issue. So basically what we have to do is every time we have a new input voltage for the DC-DC converter, we have to change these resistors. But basically what happens here, let me go back to my 4 volts, yes. So what we have, if we have a known input voltage on the beginning of this 2 resistor system, and then this is a 50k potentiometer, and this is a 100k potentiometer, and then this basically goes back directly. You can neglect the current meter here, but it goes back directly to this red connection, which is going to the feedback pin. And yeah, so as I said, first you set up your bottom of the range with the 50k resistor or potentiometer. Now they are basically the same, variable resistor. And then yeah, you keep the 100k and the 50k at minimum, and then you start to change the 50k to find your bottom. And then when you found that, you move the 100K to the max, so you see what is the top according to the trimmer potentiometer. And if you are not satisfied with that, you start to increase or decrease the output voltage. And then you go back to the minimum with the 100 kOhm resistor or potentiometer. And once you did that, you will see that your minimum shifted a little bit. That always shifts when you change the trimmer here. So then you readjust your 50K potentiometer, and then you go back to the maximum position of the 100 kOhm, and that should bring you back to the maximum position or maximum output voltage that you set up with the trimmer. So for our case, that should be 8 volts now. And it's 8 volts. So this works. But yeah, now I have 5 volts as an input here. But what matters basically is always the current in this kind of circuit. So now, as I inject 36 microamps, I have the top of my range, and if I inject 213 microamps, then I have the bottom of my range. And then, of course, this is just valid for the range, because you set the range, part of the range with the trimmer potentiometer. And previously I had 12 and 6 volts, and I had the same values here. So for the 12 volt, I have the 36 microamps, this, and then I allowed 12 volts, but we should interpret it as the maximum of our range. And when I had the 213 microamps, then I had 6 volts, but that was the minimum of the range. So this is how it works. So the first part, what I wanted to discuss, is now discussed. So the second part was basically another question regarding this. So someone was struggling with the potentiometers because they were using different values. And I said, no, that should not be a good thing, because this has to be equipped with a 100 kOhm potentiometer. And it should not really be changed. So what I will do, I have 100K, 50K, 10K, 1K, 20K potentiometer, and I believe I have some other laying around, so I will check them. So what I will do, I just remove this soldering here, and I put everything in a breadboard like here, and we will see why is it not working with other potentiometers in the same way as we would expect it right now. So let me clean up and check that version as well. So I created some order on the desk, and I also collected some resistors. So now we do the default. By default I mean we are using an equivalent resistor as this. So 100 kiloohms, see? 100 kiloohms there. And we control the DC-DC controller. I haven't changed anything, so still we have 12.69 volt in, and then you can see 12.2 out, and this is the current. And again, on the blue line we have our input. It comes into the resistor to the first pin from the left, and the middle is connected to the rightmost pin together. So we are using this as a rheostat, so variable resistor and not a voltage divider. And then this is the output of the rheostat, and then it goes into the current meter. The unit is in microamps, and then it goes out in the black wire, and it goes back towards the feedback pin. So this blue wire is always experiencing basically the potential at the output, and then here we have the drop on the red line caused by the resistor here, a variable resistor. So now I just show you that now we are at, let's say, 116 microamps, and we have the full output. So this cannot be rotated anymore clockwise, so it's on the max. So if I go down to the minimum, I start to decrease it. And first we have to notice that there is a slack in the potential potentiometer, what I mean by slack is that now I decreased the value, but still the output voltage of the DC-DC converter haven't reacted, and I can still decrease it, the potentiometer's position, so I increase the current, and still no change. So there is a slack here. You can see. So now let's do some more significant movement. Still nothing. So I almost doubled the current, but this is there still. And now it started to react. So almost at 300 microamps. And you see that now it got sort of locked, and I dropped the voltage. And now it starts to change again, and this started to give a hissing sound, so I guess we sort of messing up the circuit here. So I have to go back, and now it stopped this. And actually I can see that the LED also changes its brightness. So what could be interesting is to see what happens here exactly from this point, because now we don't have any change in the current, but we change the output voltage of the DC-DC converter. So therefore, at this range where we don't see the change and see the change here, there should be something going on with the voltage. So let's confirm that. So I'm just measuring or trying to measure the voltage, and for that I might need another piece of wire for this breadboard. Just to make everything more simple. So on this display, which you can hopefully see after I clean up. So here you should be able to see the numbers. And now you can see that the output voltage is 1.9. And you can see what I would expect in reality, that since we drop the voltage, which is injected in this part, the current is the same. So the only thing that changes is the resistance. And you see that as long as we are within the range that we are changing here, and don't mistake this with the previous experiment, because that was an external device. So here we just directly replaced the resistor or the potentiometer and not added another or two another versions. So this is different from that, but here you can see that it's very interesting that as long as you are within the range of the output voltage, the resistance, the current here is kept constant, and then the voltage which is changing across the rheostat, so across this potentiometer, this guy which I removed. And now as I hit the top of this range, then the current starts to drop, and then of course we don't get any more change here. So that was just an interesting remark. So now comes the question, what happens if I replace this resistor? And for that I just, for safety reasons, even though it's small voltages, I might kill the unit here, so I changed that. So 100 kOhm, that goes here, and let's halve this value, so 50 kOhm, and see what we can achieve. Power on. And now we go to the max, and now you can see that the current at the maximum is much higher. Of course, it's twice as much as previously, obviously, because for some strange reason the resistance of this is half of this. So yeah, it's magic. So again, we have this range where nothing happens, and now if I start to turn this potentiometer, it starts to go. And of course, when I reach the bottom of this range, this thing starts to give this hissing sound. But you can see that 50 kOhm is confirmed, and we can control this with a 50 kOhm resistor or potentiometer perfectly. At least in between 12 and 0 watt. For some fun, I could increase this, let's say 20 volts input. So we have 20 volts input, and obviously this is now changed. So we are now at the top, 18 volt. And now I go to the bottom, that is reachable. So it works on full scale basically. But I go back to 12.7. I remove this and let's go to 20K. And now it's on the maximum. The reason why you see the changes is the capacitors. Power on and 12 volt, and now we started to chop down the top because we are already running higher current. And of course we can go back to 0 and you start the hissing sound, or you start to hear the hissing sound. It's not you who starts it. 8.2, and now we have, I don't have 10, no, I have 10K. And I move it to the max. Half of the previous almost. And obviously this reaches 0. So now I have 5K. I put it to the max. And this should be around, yeah, 3 watts, 2 watts, whatever. So basically this is it. So we have the voltage all the time, of course, when we change the potentiometer to the half of the previous value. So now the maximum value is 2.79 volts, and then I start to decrease the value of this thing, and then it starts to drop. So now what I see is that it's only moving between 2.79 and 1.32, which is the minimum voltage of the circuit here. So you can see 2.79 or 78 and 1.32. And then if I would change this, yeah, I don't have the half of this, but yeah, you can imagine that I just chop down the voltage always with the corresponding ratio. So now if I go back to 50K, that's like 10 times higher than the 5K. So that should cover everything up to like 27 volts. Because the maximum with this 5K was 2.7, 2.8. But yeah, with a 50K resistor, it works nicely up to 20 volts for sure. So now I want to show you something that can give you a better idea why small values of potentiometers do not work very well. And now I keep the input voltage, let's say at 20 volts. I try to decrease it to 20, so 20.5. I can show it just to prove that I don't change anything. So this should read as 20 point something, 20.44. I hope it's visible. So this is the input voltage, and I'm not planning to change it. But now you can see that we have a 50K resistor here, and we have 18.7 volts as an output. So now if I change this to 100K, then the maximum output voltage should be very close to this 20 volts. So now 50 goes here and 100 goes in. And I have to turn it to the max. So you see that the voltage went up. So now if I change this 100K to 20K, this guy here, then our output voltage, when this is at the maximum position, it should be around 7-8 watts. 8.2. So now this was 20. if I go for 10K, it should be around 4.5 at the maximum. .5-ish, so 4.9. And then if I go for 5K and go for the max, then it should be around 2 to 3 watts. And now the problem starts here. First of all, I cannot really fit it properly. 2.79. And the problem comes here. So the problem is that for 5K, the voltage, the maximum voltage, which can be reached with this, is very close to the minimum voltage, so it starts to become unstable. And with the 1K, I would be at the minimum output voltage. So I don't know what would happen, but let's try. So you can see 1.6, and that's pretty much the minimum. So I can just barely change 0.3 watt. So what is happening? So on this side of the screen, now you can see the drawing for this buck converter. So basically this chip here, suggested by the manufacturer. And the manufacturer says that there is a voltage divider there, which I highlighted now, where there is a resistor, and that resistor is the voltage divider consists of 2 resistors, and one is, as you can see, that's the 1.2 kilo-ohms, 1.21, and the other is this 3.74 kilo-ohm. And they create a voltage divider, and based on a formula, which is basically the 3.74 divided by the 1.21, that equals with V out divided by the 1.215, which is the threshold voltage for the feedback pin, minus 1. I wrote the formula there so you can see it at once. That will give the V out. So basically, when we start to replace these two things, and the 3.74 is in principle is our potentiometer, and the 1.21 is a resistor down here, which is the nominal value is 3.9 kilo-ohms. So rearranging this equation, we can calculate the V out. And for my numbers, it was 32 watts for 100K, 16.8 for 50K, and so on and so on. You can see the numbers here. So what happens here is basically that you mess up the voltage divider so much in that circuit by using very low values of resistors or potentiometers, more precisely, that we just not able to control the circuit anymore, because we drop down the voltage, the output voltage, so much that it becomes comparable with the minimum output voltage that the device can provide. So this is why you should use high value of resistors, because then, yeah, you actually create a range with the voltage divider, in a sense that you allow higher output voltages. So I hope that this small summary of this thing was useful. So I showed you how to use this with 2 different approaches. One is that to replace the potentiometer directly, but I don't really recommend you to do that, because below a certain value you don't get any good feedback. On the other hand, if you want to fix the upper voltage limit on the output, then you can use some lower value of resistor or potentiometer, but I don't really suggest you to go down below. But using this voltage divider formula, which I provided on the video, you can just see what are the values that you should use for the potentiometer. If you want to, for example, fix the output voltage, you just use the formula, and yeah, that should work. And you will find more information on my website for this. So I worked out a few examples and you will see it there. So please visit my website. You can see the link in the description, but also you can see it here. It's curiousscientist.tech. Please subscribe to my channel because that helps me a lot to grow and help more people probably. You can also donate me if you want. You can see the picture how. And I hope really that this video was useful to you and I could explain some new things for you. I also learned some extra things here and there, so it was very practical for me as well. So I hope you like this video and see you in the next video.